Hello everyone. So today we will be seeing the behavior of a purely inductive circuit when excited by an AC source. So before that we will be seeing this numerical. So let's see this numerical. So this is a single element connected. There is a single element connected in this box, and this is excited by this voltage source, and current is drawn by a waveform represented by this equation. So we need to comment on the nature of element in this box. We need to find its value and heat loss in the circuit. First of all, this element's behavior can be understood when we see the voltage and current waveforms. Observe in the both angles. In the last class, we discussed resistive circuit. Okay, so you can clearly see that the element must be resistive. How? Both the phase angles are same, current and voltages are in the same phase. They have the same phase, and just the phase difference between them is zero. So we can say as phase difference between V and I is zero, and therefore this is a resistive circuit. Hence, element is resistive in nature. Okay, from the last class you can see. So we have commented on the nature of element in the box. Now we need to find its value. Also, you know R is equal to Vrms by Irms. Obviously, Vrms for a sinusoidal is Vm by root 2. Irms is Im by root 2. This root 2 gets cancelled out. So we are left with Vm and Im. So both the expressions are given to you. Vm, this is nothing but the peak values represented, whatever written in the front of this sign, it's nothing but its peak value. So this is 200. What is Im? Im is nothing but 10. So you easily found that it is 20 ohms. It is a resistance and its value is 20 ohms. So finally we need to find the heat loss in the circuit. That you can easily find. Heat loss is nothing but, what is heat loss? In resistance, the power is consumed in the form of heat only. So he is asking about the power. Or power, when we say in AC circuit, it is nothing but average power. Whether or not I mark this bar, it means it is an average power. So it is nothing but Irms square R. Alternatively, you can also calculate by Vrms square into R. So you can find these values. So RMS value of current will be Im by root 2, sorry. So Im by root 2 whole square into resistance is 20 ohms, sorry. So this becomes 100 upon 2 into 20. So this becomes nothing but 1000 watt, or we can say 1 kilowatt. So this is the way you can find these questions. Alternatively, you can or you can solve the exercises relevant to what we have studied till now in the back of the NCERT textbook. So 1.1, 1.2 we can solve till now, and also see the examples in the text also. These are easy, very, when you just need to find peak values and all that in those questions. Anyway, solve more questions related to that. Let us see today's topic, and it is inductance. Inductor excited by an AC source. So this is what we are going to see today, how this inductor is going to behave. And till now we have discussed resistance, inductor we are seeing today. Tomorrow we will be discussing capacitance. So these three circuits are important to understand the various combinations of these circuits. So let us begin our analysis. So suppose this is a coil excited by this AC source. This is V equal to Vm sine of omega t, and this current I am taking as positive in my marked direction. This is must be the expression for current here. So L is nothing but inductance. It is known as inductance. it is mentioned as L, and the unit of inductance is Henry, and it is also written H in abbreviated form. So this is about this circuit. Now you know that the voltage drop in an inductor, we know it is L di by dt, and you apply a minus sign in front of this so as to show the Lenz law. So minus L di by dt, this minus sign, significance of this minus sign is that whatever cause is creating a voltage drop, responsible for the drop, it is going to oppose that cause, and that's why a minus sign is seen. So if we write Kirchhoff's loop in this circuit, so we can write this voltage plus this voltage, and this voltage must be equal to 0. So we can write V m sine omega t, and this is minus L di by dt is equals to 0. So L di by dt is equal to Vm sine omega t, and di by dt is equal to Vm by L sine omega t. Now the significance of di by dt we need to understand. It is nothing but slope. Okay, the tangent. Suppose this is a current waveform. This is a current waveform. If it is a current waveform, this di by dt meaning is at any point, if you ask about di by dt, or somebody asks what is the significance of di by dt, it is nothing but a tangent at that point, and this is nothing but known as di by dt. The slope of this line is nothing but, okay. So this is the significance. Anyway, we need to calculate the value of capital I. Okay, the expression for I we need. So we need to remove this differentiation thing here. We need to integrate both the sides. So if we integrate both sides with respect to t, so it is important that we are integrating with respect to t. This time we are not going to integrate with respect to omega t as we have done it previously. So today let us see this di by dt. We are going to integrate this with respect to t so that we are left with I expression here. So Vm by L will come outside of the integration sign, integration of sine omega t. As a rule, indefinite integration we are having, so we must definitely introduce a constant. Now this constant has a significance in this analysis because as you see constant, what is the meaning of a constant here? What is its significance? We see. Suppose this excitation was not applied. At that time, if there was any current or energy stored in this inductor, or also known as initial current, the initial current in this inductor is represented by that constant. Okay. Before this, you are applied this voltage. At that time, if any current was flowing through this L or not. So I will assume here that there was no initial current in this inductor, but anyway the meaning of this constant is that it signifies if any initial value of current is present in that inductor. So I am assuming there is no initial current. You can also check the units here. This is current obviously plus current. This unit should also be in amperes. So this is a current only, and this is an initial current in the inductor. So I am assuming 0 here because I am assuming that there is no initial current flowing in the inductor, So this now becomes I. And now if I integrate this, so this is Vm by omega L, and this is integration of sine omega t means minus cos of omega t. This is the expression. Alternatively, I can write this as Vm by omega L, and in terms of sine, I can write omega t minus pi by 2. Meaning of this is Suppose cos theta, I can write it as sine 90 minus theta. But if I multiply both the sides, I can take the minus sign inside in the sine side. So I can write it as theta minus 90. So from there I have wrote this. So if you see this expression particularly, and you see your source or your voltage expression, what you observe that there is a difference of this pi by 2 term. The voltage and current now are not in same phase, they are in different phase. Before that, in resistive circuit, we saw I equal to Vm by R sine omega t, where voltage was Vm sine omega t. So compare this current equation in resistive circuit and this inductive circuit. You can easily see that this omega L is kind of equivalent to this resistance. So this omega L collectively is known as reactance. Okay, because it offers some, it behaves in the same manner as a resistance. As a resistance, if it would have been a case of resistive circuit. So this omega L, since it is an inductive circuit, and this reactance particularly is known as this inductive reactance. This is denoted by X, and in subscript we write L to show that this is an inductive reactance. Similarly, when we will discuss about capacitive reactance, we will mark it as Xc. So anyway, now we say that this is inductive reactance. So, and now if you see the phasor diagrams, you can conclude easily from the expression also that both the current and voltages are not in the same phase now. Okay. So suppose this is the phasor I am considering for voltage. So this angle, suppose it is omega t. Okay, so current phasor is omega t minus pi by 2. Okay, so suppose it is like this. Okay, this is the, and phase difference between them is 90 degrees. So if Vm sine omega t, then current you can easily see from here, I is equal to Im sine omega t, this, okay, this omega t minus 90. Then you can get the expression for, you can get the phasor for current. This kind of a phasor we can see. Alternatively, you can draw the phasor in this manner also. You can take reference generally a voltage or current, any one of them is taken as reference. Suppose if I am taking voltage as the reference phasor here, then with respect to voltage, current is lagging with respect to 90 degrees. So this is also a more appropriate way to show the phase difference. Normally this kind of format is used more and is more convenient to use. Okay. Anyway, the purpose is that if you rotate this phasor diagram anticlockwise, always voltage will be ahead 90 degree of current, or current will be lagging with respect to voltage. So two conclusions you can write from here. Okay. A conclusion you can write from here. One conclusion you can write from here is that in purely inductive circuit, the current lags the voltage by, this is important, it is lagging. If I am taking voltage as reference, by 90 degree or pi by 2 radians. This is important. Okay, now let us see the power. So expression for power we will write. So generalized form P equal to Vi, that is Vm sine omega t into Im sine omega t minus pi by 2. Again, I can write this as Vm Im sine omega t, and if I can write this as minus is back to the earlier form, that is minus cos of omega t. Why? Because I need to use an identity here, which is suppose 2 sine A cos A. I am clubbing this into only one trigonometric form, only one sine or cos, so that we can analyze the expression. Here are two sinusoidals in multiplication, so we are reducing that. Okay, to sine A cos A, so it is sine 2A. This is the identity. So in order to use that, we will be multiplying in numerator and denominator 2. 2 will be multiplied in the numerator, 2 will be multiplied in the denominator. So this 2 will be consumed in this identity. So we will be left with minus Vm Im upon 2, and in multiplication it is now becomes time to omega t. So now if I need to find average of this, okay, ultimately average will be what? Minus Vm Im by 2 average of this. Clearly, for a sinusoidal wave, the average value will be 0. Hence, this power, average power in this inductive circuit will be 0. Or you can understand this better. So, in this way also, suppose this was omega t. Now, sine omega t, now the frequency is doubled. 2 is multiplied here. It means the time period is now half. The time period has become now half. So this is at pi only one cycle is getting complete. So this time period now is pi. So if we want to find in that way, we can also find in integration form. If you need to find in that way, you can write Vm. Generally, when write by writing a reason here, yes, that the average value of this sinusoidal function over a complete cycle is 0. So the average power calculated is 0. Alternatively, if you want to follow the integration path, you can follow this manner. So now, this is now integration of sine 2 omega t. I will be integrating with respect to omega t because I am writing the limits in terms of pi. So now the cycle is from 0 to pi only. Since frequency is doubled, now 1 upon pi. This is the average value. So if I am considering this by 2, you can write sine 2 omega t integration is minus cos 2 omega t by 2. So 2 will come outside of here and you will be left with cos of, and minus will also come. Okay. So minus I can write outside cos 2 omega t, and the limits are from 0 to pi. So you can see cos 2 pi is nothing but 1, cos 0 is nothing but 1. So 1 minus 1 will be 0. Ultimately this is 0. So the average power is 0. So in case, unlike the case of a resistive circuit, the average power here is 0. There the average power had a certain value. Because the average power here was, there was something, a term called 1 minus cos 2 omega t by 2, and the average value was there, some half. Okay. But this is not the case here. The average power value is 0, and we will see the analysis now, waveform analysis we will do. So we can understand this better. So let us see the waveform. And with this waveform, we will also see how this inductor is behaving in each different cycle. Suppose this is one cycle, omega t I am saying, and this is suppose your V, the white curve. And let us mark the different benchmark values of omega t. Let us see this. This is pi by 2. This is obviously is. This is nothing but pi. This is nothing but 2. This is 3 pi by 2, and this is nothing but 2 pi. So let us draw the waveform for current. So current is lagging 90 degrees with respect to this voltage. So it will begin from here. After 90 degrees, we will start the curve for current. So it is behaving in such a way. Okay. So I will complete the cycle of current. So I will write like this. Okay. So I will extend this graph here so that I can write the complete cycle of current. So let us assume this is another 2 pi plus pi by 2, that is 5 pi by 2. This is 5 pi by 2. So let us see this. Now we will see the power. Okay. Yes, let's retrace back this. And this is say point number 1. This is say point number 2, 3. This is 4 and this is 5. This point. Now let us draw the power curves. From here to here we see voltage is positive. See, P is VI. So if one is positive, one is negative, it means power is negative. Both positive, it means power is positive. This peak will be this only, okay? Anyway, sinusoidal waveform we got sine 2 omega t terms. It is sinusoidal in nature. We have seen in the instantaneous waveform. And this is now again positive current, negative voltage. So again power will be negative, one positive, one negative. Now both negative, so this will be positive. Again one positive, one negative, so again negative. So it is sinusoidal in nature power. Now you can as easily see this green curve. The power curve is sinusoidal and the average value of this sinusoidal curve is 0. That's why we got the average power as 0 in an inductive circuit. Now let us see what is happening between these key this key benchmark points I call, because we will see how this inductor will be behaving. Okay, initially I will see from this point as from 0 complete one cycle of current. I will be seeing how this inductor is behaving anyway. So this is the current. So this is going down. Up. So this is down. Anyway, if I see the flux line, according to right hand rule, you can write the flux lines for this, draw the flux line for this. It will be in circular fashion. Let us do 2 of them so that I can do a comparative study. Let us have this, and by right hand rule, if you find the flux line, they will be, if you are in curl direction, if you see your fingers, and thumb will be indicating the flux line, so this will be like this only. So this is the direction of flux, suppose. Okay, anyway, we need to understand that now here, as let's see from 1 to 2 position, in between 1 to 2 interval, current is increasing. That is, the slope is increasing, the current is increasing. Positive di by dt, voltage is positive, current is positive. First of all, power is positive. Power positive means power is absorbed. And when it will be negative, you will say it is delivered. So power is absorbed, and moreover current is increasing. And as the slope is increasing in this manner, we are seeing that flux line will be, flux is developed, and we say that this inductor is magnetized. So magnetization is occurring here. Magnetization of inductor you can see easily. Let us see from 2 to 3 now. What is happening in 2 to 3? Now voltage has become negative now. Since voltage has become negative, current is positive, power is negative. Power is negative, it means it is now delivered. In this range, the power is now delivered. And secondly, you see the current from 2 to 3. Current up till after this point, the current starts to fall. This is a decreasing slope. Okay, it is now the slope will be, you will say di by dt is now here falling. So you can say that demagnetization is occurring. What will happen? Current will continue to flow in this direction, but this current will be in decreasing nature. This current will be decreasing, so this flux line will now be becoming less and less and less. So that's why it is now doing demagnetization. It is going in demagnetization state. Similarly, from 3 to 4, if you see 3 to 4, what is happening? 3 to 4. In 3 to 4, if you see, what is happening in 3 to 4? Let me just adjust this. In 3 to 4, both current and voltages are negative. That's why power is positive. So if power is positive, it means it is absorbed again. And if I see power is absorbed, current is now becoming, after in previously it was decreasing, it decreased till 0, till 3. Now it is further moving in this direction only. Current is becoming negative, but it is increasing in this direction, negative direction. It is increasing in negative direction, or the slope is now increasing in opposite direction. That's why we will say current is now reversing and it is increasing in the reverse direction. And so that's why we will say it is demagnetization is occurring, but in opposite direction. Okay, opposite direction to this previous direction. The coil is becoming magnetized. Coil is becoming magnetized. Magnetization is occurring, but is occurring in the opposite direction. The coil is undergoing magnetization, but it is in the opposite direction. Now this current will be reversed. For this, you can say that this now current, this everything will be now reversed. 3 to 4. If this was down, now this was supposed to, it is going to be up now, and this is down. So if it is up, this is going to be down now. So alternatively, this is down, this is going to be in this direction. So this is going to be now reversed. The flux is getting reversed now because the current is magnetization is going on in the opposite direction. So that is the meaning. And alternate, finally we have the 4 to 5 interval, and here you can see that now the current is going towards 0 again. First of all, the power is negative because it is, you can see the graph, power is negative, so it is getting delivered, and magnetization and demagnetization, what is going, we are going to see. As compared to previous state, this was going magnetization in opposite direction. This coil was magnetizing in this due to this increase in current in the reverse direction. Now this is going back to 0 again. So this is going again under demagnetized state. Compared to this previous interval, this magnetization is now being opposed. It is going demagnetized. Coil is getting demagnetized because the current is now reversing again, and again di by dt is changing in the opposite direction. Once here the di by dt was going like this, again di by dt now falling like this, again increasing in opposite direction, di by dt is here. So this you can understand well. So conclusion is that in each interval, you can see in different intervals, power flow is also getting altered. In one interval, it is positive, again negative, positive, negative, delivered, absorbed, delivered, absorbed. Between source and inductor, this game is being played with the sinusoidal supply. In one time, it is getting absorbed, again delivered, absorbed, delivered, absorbed, delivered. And when we talk as a whole, the power is 0. Okay. So there is no power consumed in an inductive circuit. This is the conclusion. And this magnetization of the inductor is continuously happening. So today we have two conclusions. This inductive circuit we can write in this comparative form. This is, suppose I discussed resistive circuit, and this is inductive. Purely resistive, purely inductive circuit we have discussed. So let us write the points. Suppose in resistive form, this is the resistive circuit, this is the voltage, current is always in phase in resistive circuit. But in case of inductor, if the voltage is at say particular angle, the current will be always 90 degree behind the voltage. And second thing is that here R is the resistance in the circuit, here omega L, also known as XL, is the reactance of the circuit. These two terms are also important. Another point is that the power, average power in this was not 0, it was some value, it was IRMS square R, We also saw the graph like this. This is pi, 2 pi, 3 pi, like this power graph, and the average value was not 0, it was some value. But in this case, the average power is 0. We saw the waveforms also. It is sinusoidal, and in both the case, we saw that the frequency was doubled. Okay, the frequency was doubled. This here also the frequency was doubled, as we see that of voltage and current in comparison to voltage and current. The frequency of power, the power curve, you can see the frequency was doubled. But here the average value is 0, plus minus these all cancel, and but here we have a definite value of average power. This what we saw. So this is what we have learned till now. In the next class we will see capacitive circuit, how a capacitive circuit will be behaving when excited by an AC source, a capacitor. Let us continue in the next lecture.